The first topic of this module introduces the importance of water flow and the effect of hydrologic regime on entire ecosystems. It explains terminology and gives an interesting perspective on the way flow information is organized and communicated. The differentiation between observations, estimates, and actual measurements is also described. The second topic shows a decision flowchart that might help you navigate through the options based on your purpose and channel conditions. The third topic shows demonstration videos of flow measurements and discusses advantages and disadvantages of each type of method. Click on a topic to start, or click the next button to see them in order. Welcome to the Flow Measurements module. As you can see by the activity highlighted in green on your screen, flow measurements are usually done last in the series of field activities, after water quality measurements and sampling activities have been completed. Flow measurement may involve wading in the channel. This module provides a basic overview of stream flow and how it can be quantified. Stream flow is an extremely important parameter to observe, estimate, or measure in combination with other water quality characteristics because it is essential for data interpretation. Click on a topic to start, or click the next button to see them in order. Stream flow, or discharge, is the amount of water that moves past a fixed point during a given period of time. It is a crucial component of a stream ecosystem, intimately connected with a wide range of physical, chemical, and biological processes. There are many techniques for measuring flow, each with advantages and limitations that depend on field conditions and the questions to be answered. Flow may be described in terms of different time scales. The basic unit is a flow discharge measurement at one place at one time. This is normally called instantaneous flow. Many flow discharge measurements can be combined to create a hydrograph, a record of changing flow for a selected period of time. Hydrographs are developed from repeated measurements at one location and may be determined in various ways. For a single storm, or a span of time such as individual years or seasons, or as statistical averages of many storms, years, or seasons. Flow regime refers to patterns in a stream's hydrographs, whether natural or the result of human activities. Characteristics of flow regimes that might be important for stream assessment include annual peaks or lows, duration of peaks or lows, and average time between recurrences of a particular size storm. Why is it important to know the flow? Flow is linked to conditions throughout the watershed and affects many aspects of aquatic systems at all of the above time scales. Instantaneous flow tells us about the wetted area of stream and amount of aquatic habitat present, the increased or decreased number of organisms that prefer certain velocities, the aeration of water and the amount of dissolved oxygen available for aquatic organisms, the stability and level of water temperature, the dilution of pollutants entering the creek. Hydrographs of changing flow are used to document and predict the frequency and extent of flooding, the dislodging of flow-sensitive organisms or microhabitat structures, the distribution and transport of pollutants along the creek, the erosion and movement of sediment from creek beds and banks. Flow regime understanding is important in considerations regarding the seasonal or annual water supply to the stream and surrounding riparian zone, flushing that reduces the silt or debris that clogs some habitats, for example, spawning gravel, groundwater recharge, the requirements of animals and plants at different ages during their life cycles, long-term channel forming processes such as downcutting or siltation. The contents of this screen were taken from a fact sheet developed by members of the Flow Work Group, established by the Technical Advisory Council for Citizen Monitoring in 2000. Observations, estimates, and measurements are three options used by SWAMP for capturing flow information. All three options are based on the concept that flow of water through a pipe or a channel, commonly called discharge, or flow rate, or flow discharge rate, can be quantified as the volume of water that passes through the pipe or channel in a unit of time. However, the way they are recorded and reported is different, as you'll see in the next three screens. The first option is to observe the stream and choose one verbal category that describes it best. The common categories offered for flow conditions or observed flow are as follow: dry water body bed, isolated pools, trickle, and waterway full, no observed flow. These categories include language for communicating zero flow and no flow situations, with detail that is very relevant for data interpretation, detail that falls between the cracks when only numerical flow data are captured. Observations are not intended to yield numbers, but when one of the offered verbal categories is recorded, that result can easily be used in a database. The 4 categories on your screen are currently used in the SWAMP datasheet, but you can construct your own with additional information that fits your needs, such as more than 5 gallons per second, or at bank full. Please note that observation options for moving water are based on visualization. They do not and cannot include information on the magnitude of the flow beyond a given perceptible range. For estimates of magnitude, you need to use another set of categories, as you will see next. The second option is to estimate the volume that passes through per unit time, either by visualizing water going into a container and estimating the time it would take to fill it using the virtual bucket method, or by estimating the average velocity of objects moving with the water and the average dimensions of the channel cross-section, both width and depth, and then computing the estimated volume using the visual estimate method. Well-trained operators can do this when they are using skills acquired from previous experience in actually measuring these things again and again and again. The results of flow discharge estimates may be called estimated flow and reported as a numeric range category. For example, if the estimate yielded about 12 cubic feet per second, it would fall within the category of 5 to 20 cubic feet per second. Estimates must be distinguished clearly from actual measurements, so it is not recommended to report them as single numbers. The SWAMP datasheet currently calls for measurements in cubic feet per second, but numeric range categories can be given in other units, if required by your database. Because observations and estimates are mutually exclusive in most cases, the current SWAMP datasheet includes a combination of verbal and numeric range categories from both boxes, under the characteristic name Observed Flow. The third option is to actually measure the volume, velocity, channel dimensions, stage, or any of the other characteristics required to compute the volume that passes through per unit time. The results of flow discharge measurements are given in numbers, volume per unit time, but each one is generated using actual measurements of the needed characteristics, with the known range of error around it. Stream flow can be calculated based on the water level you can read on the staff gauge, if you have an established discharge rating curve for that location. Take a look at the flow information paper in the SWAMP toolbox, or on your CD for more details. The rest of this module is focused on this third option, flow discharge measurement. When you are trying to find the best method or device that will work for you, you will find the caveat for flow. Whereas the selection of other kinds of field measurements depends on anticipated operators' skill, time availability, and funding, you have to consider additional factors when selecting a method to measure flow. Often you do not have much choice in finding the right cross-section, or a smooth run having the length needed for using the float method. You cannot control the flow conditions either, and these dictate whether you will be able to wade or not, such as for high-end flows, or whether you can use a meter or not, as for low-end flows, or trickle. The chart on your screen channels these decisions. It was developed by members of the Flow Work Group established by the Technical Advisory Council for Citizen Monitoring in 2000. Click the graphic to see a larger version of it. In an ideal rectangular channel, the flow rate can be computed from the current velocity in feet per second and the dimensions of the channel. Channel width in feet and the depth of the water in the channel in feet are used to compute the active cross-section of the channel. The volume of water displaced is computed from the velocity in feet per second and the cross-section area in square feet. Essentially, it is described in feet times feet divided by seconds. This unit is called cubic feet per second, or CFS for short. This really means that at 1 cubic foot per second, 1 cubic foot of water is moving through the cross-section in 1 second. However, nature creates complications. Current velocities vary in different parts of the channel, and stream channels are never made of ideal rectangles. This is a very good thing. Go to the next screen to see how to address it. As you recall, the centroid of the flow is where most of the water goes, where you want your kayak to be when you approach a riffle, or what you want to keep out of when you are in a sharp bend under hanging vegetation. You know that the water there is moving fast. Now, suppose your centroid is in the deepest part of the channel, as shown in example A on the left of your screen. If you take one measurement of velocity and depth in the centroid and apply it to an imaginary rectangle that represents your cross-section, you will be making a lot of approximations, and your flow measurement result will have high uncertainty. However, the cross-section can be divided into smaller pieces as you see in example B, and the velocity and depth can be measured in each one. The flow discharge for each segment is then calculated separately, and all the segments' flows are combined to compute the total flow. The more segments you have, the more accurate your total will be, because you are plugging in more real numbers and averaging less. USGS recommends dividing the cross-section into at least 20 segments, each one representing 5% or less of the total flow. Also, as you know, the water at the surface runs faster than that close to the bottom, so you need to get an average velocity that represents the entire water column. In shallow water, less than 2 to 3 feet, use the convention that the point representing 60% of the water column, as measured from the surface, is where the average velocity occurs. USGS calls for 2 velocity measurements if the water is deeper, one at 20% of the depth and another at 80%. Please look for more information in the USGS course referenced at the end of this module. So, how do you measure the width, the depth, and the current velocity? Devices to measure cross-section dimensions include yardsticks, tape measures, stadia rods, or any other appropriate length measuring instrument. Current velocity can be measured with a floating object or with a meter. When you use a floating object, also known as the float method, the velocity is measured as the distance traveled by an object per unit of time. When you use a mechanical velocity meter, the flowing water rotates a moving part, and the circular motion is translated to velocity units. You can also use one of several types of electromagnetic current meters, which sense velocity based on electrical currents in magnetic fields. Click on the top button to see a demonstration of the float method, or click the other button for a velocity meter demonstration.
Okay, Sean, I'll walk down here and place the tape at the end. Okay, and we want 20 feet. Are we good? Let's check this one. $20 feet? Good. Okay, let's see that form.
Yep.
34. It'd be 42. Yeah.
Yeah.
03. Zero, 10. Yeah.
Yeah.
43. 51.
51.
Did you notice that thing went in this little eddy here? Slowed it by a second.
It's all in the release. No.
13. 21. This clip is a demonstration of the measurement of a flow across a wadable stream using a bucket wheel velocity meter and a handheld readout device. Here you see the team reconning the stream. The idea here is to find a suitable place to measure the flow. The bottom should be fairly even. The sides of the stream should be even as well. As you can see, this is not a very good place because there's a couple of rocks there. So the crew is moving upstream, finding a suitable location. And I think here they've found what looks like a good place. And the first thing they want to do is make sure that, in fact, there are no big obstacles in the bottom or obstacles on the side of the bank. And then they measure the width of the stream using a non-stretching tape. And you can see the one team member has anchored the tape on the far bank, and then the tape is anchored on the closest bank, stretched tightly. The idea here is to have 5 equal increments across this particular stream. So one of the team members is going to mark out each increment with a clothespin on the tape, and wading across the stream, he is placing a clothespin at each one of the chosen increments. Then at each one of those points, they will make a flow measurement. And now, at the first increment, the wading was placed firmly on the bottom, held vertically, and then using the vernier scale on the handle, the rod is adjusted upwards to 60% or 0.6 of the depth measured at that point. There's a small wheel that is turned by the current. Here you can see the wheel on the rod. We're going to zoom in now and take a look at that, and you can see the wheel rotating, the current rotating the wheel. And each time the wheel rotates, it makes a click, an audible click in the earphones, and also digitally records a increment in the handheld recorder. The number of rotations is counted per unit time, usually 1 minute at each site, and then that is integrated to a velocity at that point by the software in the handheld device. And now the device is moved to the next site, and again placed securely on the bottom underneath the marker. Held vertically. It's very important to held vertically, and the measurement head is perpendicular to the flow of the current. Then the total depth is measured, and then using the vernier scale on the handle, the measurement wheel is raised to 60% of the depth, and the process is repeated again. Each time the process is identical at each one of the marked intervals along the tape.
If you are thinking about selecting a way to measure current velocity, You might want to consider the advantages and disadvantages of each approach. As you recall, when you use the float method, the velocity is measured as the distance traveled by an object per unit time. That object can be an orange peel, or a lemon, or another clearly visible object of density slightly less than water. There are advantages. A, the floats do not cost much, and B, they are readily available. The disadvantages are as follows. A, floats float. They cannot be deployed at a desired depth below the surface. B, a float does not navigate. It is carried by eddies, so it is usually not possible to control its course of movement in the channel. C, the method requires a longish stretch of straight channel for the float to travel at least 20 seconds, and that may not always be available. When you use a mechanical velocity meter, the flowing water rotates a moving part, and the circular motion is translated to velocity units. Mechanical meters utilize horizontal axis impellers, such as Vailport meters, or vertical axis cups, such as Price Type AA meters. These meters can be rigged to a handheld device, or suspended from a wire with a hefty weight underneath them. The advantages? A, they can provide separate measurements of velocity, because we can control the measurement location and depth. And B, if well maintained and frequently calibrated, they can generate data of high accuracy and precision. The disadvantages? A, they require great care in handling and storage because they are fragile and finely balanced. B, they malfunction if algae or other objects get tangled in them. C, they can be used only in situations limited to wading or suspension from a bridge. And D, they cannot measure trickles. Electromagnetic current meters are based on Faraday's law, which states that a conductor, such as water with salts in it, moving in a magnetic field, which in this case is generated by the probe, produces a voltage that varies linearly with the flow velocity. Electrodes in the probe detect the voltage generated by the flowing water. The common shape of electromagnetic probes, like the Marsh-McBurney meters, is that of a truncated teardrop. These probes are sometimes called velocity sensors, although that term is mostly used in conjunction with media other than water. Electromagnetic meters have roughly the same advantages and disadvantages as the mechanical meters, but their compact shape and lack of moving parts is another advantage, and the potential for sensor fouling is a minor disadvantage. Because natural stream channels are not perfect, when flow rates fall below 20 quarts per second, a little less than 1 cubic foot per second, it often becomes impossible to measure current velocity, no matter how tiny or pygmy your propeller is, or how agile your orange peel is. If you need to know what the flow discharge is, you can channel all the flow into a container and measure the time it takes to fill it. There are several protocols you can use for this.